Scanning electron microscopy. What type of microscopy is this? What's the finest resolution we can zoom into? What people use it for? And why? Let's dive into the world of nanoparticles and explore what is scanning electron microscopy, or SEM, and how we use it. People be using the light microscope for a long time. Light microscopes, it's the normal microscopes we get accustomed to. The ones to using the light emitted by the object, collecting the light beam, and showing our very fine objects. For example, it's very common in biology. We use the microscope to observe objects and the elements which we cannot see with the naked eye. We have a limit of the resolution we can see with our eyes. Even if you have specific vision, for example, people short-sighted can see a little bit better smaller objects, not as the people long-sighted. However, they're still limited. And it all depends on how I observe the light, beam of light that come to our vision field, and also the wavelengths of the light. We cannot see anything smaller than the wavelengths of the light emitted. Therefore, we can magnify things up to 1,500 times, and we cannot see anything smaller than 0.2 micrometers. Micrometer, it's the 1/1,000,000th of the meter, or 1,000th of a millimeter. People have been using the optical microscopy for a long time, for almost 4 centuries. People use the magnifying lens glasses, and with the source of light you can see the object. However, since the physics progressed in the beginning of 20th century and we discovered the electrons, the atoms, the composition of the molecules, we could start using the electron microscopy. In the electron microscopy, instead of light beam, we use the electron beam, and we're scanning the electrons emitted from the objects or the surface. The focus being directed to the surface, magnified, and scan the surface, and whichever electrons which are moving around its atoms will be replaced from the shells or the clouds they are rotating around the atoms. They will stay in the chamber where is the vacuum, and detector will absorb them and scan. We'll have the image of the surface depending on how many electrons we register. Usually we use scanning electron microscopy to map the surface topography of a sample. The electron beam is scanned in a raster scan pattern, and the position of the beam is combined with the intensity of the detected signal to produce an image. Usually we use the secondary electrons emitted by the atoms, excited by the electron beam, and is detected by secondary electron detector. And based on its number, we'll have a different signal and the color on the image. Therefore, we can zoom into a resolution better than 1 nanometer. People start using the first microscope like that back in 1930s, and since the 50s of last century, the electron microscopy became widespread among scientists and used widely. The new science branches appeared, new research, a lot of discoveries was made, and people could observe first time things like the human genes and make revolutionary discoveries in the bacterial world, viruses, in physics, geology, engineering. Let's figure out how fine each nanometer is. It's very hard to understand this because we cannot see it with our eyes. We all can imagine how big is the 1 meter. So in this 1 meter, we have 1 billion nanometers. It's very hard to operate in these numbers. Let's look closer. If we look in the 1 centimeter, which is 1/100 of a meter, 1 millimeter will be 1/10 of that. Now let's dive into something finer and harder to understand. 1/10 of a millimeter will be the thickness of the average hair on your head. And the 10 times smaller than the thickness of your hair will be the red blood cell. It will be about 10 micrometers. 10 times smaller than red blood cell will be the 1 micrometer, which is the size of bacteria. The virus is even smaller than 1/10 of the micrometer, or the bacteria. And the 10 times smaller again will be the cell membrane, which is about 10 nanometers. And now we'll talk about sizes like 1 nanometer, which is here you can see it's the approximate size of sugar molecule. Therefore, the modern scanning electron microscopes can look at something finer than 1 nanometer. The best resolution was, with a very good sample preparation, observed about 0.2 nanometer, when you can more or less see the image or the shape. Let's, for example, look in the wing of this butterfly. It has amazing light refraction. It has a little traps on every cell of its wing, which absorb the yellow light from all the light which received by the wing, and will therefore emit back only the blue light. Therefore, the wings of the butterfly always look beautiful, bright blue, although in reality they're not of the blue color. With the optical microscope, we can go down to less than 1 millimeter, less than even half millimeter, quite fine resolution, although it's become very blurry and you cannot see the features clearly. Clearly wouldn't see the straps for the light. Let's observe it under the scanning microscope, and let's zoom deeper into these features, which look like a line on the optical microscope. When we zoom more, 100 times, we see little cells everywhere. And when we zoom more, to about 1000 nanometers, you can see the structure of these cells which trap in the light. The resolution here can go up to tens of nanometers. You can see the features on the wing of the butterfly. Let's zoom into the microchip. The microchip you can find in every electronic objects right now. You use your notebook, your cell phone you're watching this video on probably, television, computer, desktop computer, and other electronic devices. If we're looking into this chip with the optical microscope again, we couldn't see as fine, but underneath this surface there's a network like a megapolis city, highways, intersections, towns. With zooming, we can get into up to 6 micron resolution. And there you can see even finer objects, which can go up to the 1 micron size. This is interesting that nanotechnologies can go even lower in resolution. And you can see there that the modern chips can go smaller than 1 micron in size. 1 micron will be 1000 nanometers in size, and you will see that there are about 20 nanometer transistors could be put into one. That's the technologies we can have these days. For this, give you an idea about the resolution that scanning electron microscopy gives us. There's also transmission electron microscopy, TEM, and I had opportunity to work with those. They work slightly different, and we can talk about this in future videos, so you can just research about them yourself. But they required you to prepare a very thin sample, and the beam will go through the sample, and according to the shadow, you'll build the image of your electron field. With scanning electron microscopy, you can hear from the name, you can scan in the surface and you can create topography of the objects. Therefore, we can use it for things like small animals, insects. You can see the eye of the fly or some bugs. We can see things like cells, viruses in 3D. Many people creating even 3D images, so they're photographing the same field from different angles and creating beautiful 3D image you can see with the special 3D glasses. I had the opportunity to work with those. Photographing some things, animal object for 3D representation, it's a lot of work because you have to find good angle, don't make it too wide or too narrow. Since then, I really appreciate when people make it 3D movies. It's such a hard job. Therefore, the scanning electron microscopy have a great advantage. We can see much smaller things than we used in optical microscopy and can give us topography. It doesn't give us a light because we're building image just a black and white and grayscale of black and white rather than the color, true color, because the color it's the light. And electrons which we detected, they don't record it as a light. But you can color your images later using the modern programs. However, usually we created black and white image, but we can see clearly the topography if the sample were prepared very well, so you don't have extra electrons on the surface, you grounded your electron in specific resin, we call it proxy, and you coated it. We usually coated all the samples with metals like gold or something else to create good refraction, and usually gold the best material to coat it, especially organic objects. So you have plentiful good free electrons you can scan. However, the limitations are that because there's a vacuum, you have very steady sample coated, you cannot observe the live objects. In the normal optical microscopy, we can look on the live objects. We can see how the wire is developing, or cells, or some eggs of some insects, and so on. And you can record it in a live motion. With the scanning electron microscopy, everything has to be dehydrated, coated, and placed into the vacuum chamber. However, the main advantage, and I repeat it again, will be the limits of the wavelengths we can record it. The electron wavelengths much finer than for the light beam, and it's on a finer spectrum of our wavelength spectrum. Those waves, the ones that we cannot detect with our eye. Therefore, with developing computers and physics, we could use now the microscopes. I came across SEM through my studies too, and it's actually played a dramatic role in my research. I was looking on the very small nano-sized particles in sediments, in the valleys, coming from different environments, comparing them and creating the patterns. There was a big research done in 70s, 80s about the sand particles, just the fine particles, usually hard crystals which you find in the sand, for example the quartz, which been grounded through its travel, depends what it is, for example if it's been in a river or under the ice in a glacier or on the slopes or on a beach. It will create different features on the surface of those grains, and they'll be all recorded there, and you could see them under the not normal microscope but scanning electron microscope. And people created a whole field of research, even atlases of the scanning electron microscopy surface features of the sand particles. I dive into that and spent several years preparing my samples, which take a lot of time, and looking them under this SEM. However, I have some revolutionary discovery which I didn't aim in the beginning, but at the end it was the main discovery of my research. I talked about this a little bit in my previous video if you're more interested. But let's come back to SEM. So the SEM, it was like a whole facility at my university, and usually you can find it around many universities around the world, And they're usually located around biology or medicine departments where people more commonly use those microscopes. So they observing different bacteria, viruses, playing with things like that, or observing some cells of animal or human, looking at disease and so on. And that's the main use, I think, probably today of SEM. However, it was amazing how many people used SEM and TEM, transmitting electron microscopy, for engineering purposes. We can see amazing feature of elements of the crystals on the surface. For example, if you have some kind of new material you creating for, I don't know, building construction or engineering or for microchips, you will use your SEM to see how it's behaved, how it's corroded, which material is strong or not, discovery of the graphite or something like that. For example, people observed the features in our world around us, like this lotus leaf. Everybody knows that lotus leaf do not get wet. And many people suggested maybe there's special chemistry on its surface or oils. Actually not. It's just a feature, topographic feature of its leaf. Similar like a velvet cloth, which doesn't get very wet easy. It has number of very, very fine hairs. And when you zoom into, they're not even of the size of millimeters or sub-millimeters. They're of the size of the micron and less. And we just talked about how fine it is. It's very fine. And they created a field of many, 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 many hairs of this size and the air in between, which not allowed to the surface energy of the water to contact with it. So the water preferred to stay in a bubble with itself rather than contact with the surface and making the surface wet. And the attraction between the water molecules greater than the attraction between the water and the surface. So the water stay away. There's thousands of nano-size hairs on top of those bumps. Since we discovered that, people start using this technology to create some special materials for our use. Researchers start creating hydrophobic fabrics, which repel the water, or self-cleaning coating, and the surfaces which can repel the water to filter some elements out. So we can see how many other things we can observe with using SEM. They're just examples of few. And as I said before, mostly used in biology, medicine. The SEM is very useful for engineering and geology. We can even detect the objects which come in from the space using the SEM, but that will be the subject for the next video. I hope you have a brief understanding of SEM, how it works, its history. If there's interest, we can talk about this in detail in the future videos, because I have things to say about it from my personal experience. I hope you enjoy this little show of the videos I prepare for you. Like it, share it with everyone who might be interested, and I'll see you in my next videos.